All right, today we're going to look at section 11.3, trig substitutions. So recall these basic facts. And remember that this can be proved, and both of these can be proved using really the only two trig identities that we're going to need to know, other than the half angle formulas from last time. Sine squared x plus cosine squared x equals 1, and the related version, tan squared x plus 1 is secant squared x. Also recall that the derivative of tan x is also secant squared x. So these things are things that we're going to need to know. And remember, this one I'm sure you know. This one is just really just an alternate version of this first formula. If I take that first formula and divide through by cosine squared, then I get this. And this is something that we can obtain by using the quotient rule. Tan is sine over cosine. All right, now, so let's look at some more complicated versions rather than just these two basic ones, which really would have been proved in the Calc 1 class. Let's look at 1 over 9 plus x squared dx rather than just 1 plus x squared. So remember that the basic idea, so here's our trick, right? We're going to apply a little trick. If I can make this x squared, I want x squared to be 9 tan squared of something, our new variable theta. Because if that's true, then 9 plus x squared is 9 plus 9 tan squared theta, which is 9 times 1 plus tan squared theta. And by our formula, 1 plus tan squared theta is secant squared theta. So I get 9 secant squared theta. So the idea here is to put something in for x squared, which simplifies the denominator. And if we choose this, we can factor out the 9's, and we get 1 plus tan squared, which is secant squared. All right, remember, we can't forget about anything else. We also need, if we're substituting stuff in, this denominator then is going to become 9 secant squared theta. We also need to know what dx is. So this is why the dx, this is where the dx starts to become very important. And so if I need to know dx, then I need to know x. But if x squared is 9 tan squared, then x is 3 tan by taking the square root. And therefore the derivative, by taking the derivative, constant goes along, derivative of tangent is secant squared theta, and don't forget about the variable that you're taking the derivative with respect to, d theta. And in that case, our integral becomes 1 over 9 plus x squared, which is 9 secant squared, dx, which is 3 secant squared, theta, d theta. The secant squared and the secant squared cancel. The 3 and the 9 makes a 3, and we get integral of 1/3 d theta, which is 1/3 theta plus c. But our original question was in terms of x, so we better give our answer in terms of x. So I need to know what theta is. And to figure out what theta is, we're going to go back to this equation right here. If x is 3 tan theta, then x over 3 is tan theta, which tells me that by putting tan inverse on both sides, tan inverse of x over 3 is theta. So my final answer will become 1/3 tan inverse x over 3 plus c. Let's look at another one. Say 1 over 1 minus 4x squared dx. Remember that if this were just an x squared in here, then the answer is going to be sine inverse. And so that suggests that we're going to use a sine substitution rather than the tangent that we saw a minute ago. And I'll summarize these things in the end. But the idea here is if I can turn this piece, I want this piece to be sine squared theta, so that I get 1 minus sine squared theta, which is cosine squared, and then I'm taking the square root, and that'll turn it into cosine. So I want 4x squared to be sine squared theta, which means that x squared is 1/4 sine squared theta, and x is 1/2 sine theta. We need two things out of this. We need to substitute in for everything. So that tells me that the square root of 1 minus 4x squared is the square root of 1 minus 4x squared, which is sine squared theta. Well, that's square root of cosine squared theta, which is cosine theta. We also need dx. dx is the derivative of x. 1/2 is a constant. It goes along. Derivative of sine is cosine. But dx, it's really dx d theta, derivative with respect to the variable theta, so theta also comes up, and we get 1/2 cosine theta d theta. And now we can substitute everything in. Right, so this denominator is the square root of 1 minus 4x squared, which is cosine theta. And we also have dx right here. So this becomes integral 1 over, that's cosine theta, and dx was 1/2 cosine theta d theta. Cosine thetas cancel. Integral of 1/2 d theta, which is 1/2 theta plus c. Finally, we need to evaluate theta. But so then we still need to solve for theta. In order to solve for theta, we go back and look for our x equals that we had somewhere previously. And since this whole mess was sine squared, that tells me that x is actually, we discovered that x was 1/2 sine theta. And if x is 1/2 sine theta, then 2x is sine theta. And so sine inverse of 2x is theta. And I can substitute that back in for theta, and I get 1/2 sine inverse 2x plus c. All right, we'll look at one more right now. This combines both of those tricks that we need all at the same time. Right, so if this were just a 1 plus 3x squared. Remember the very first example, 1 plus x squared was a tan substitution. So this is going to behave like a tan substitution. We just got to figure out what it is. Really what I want here is, since that's not a 1, I'm going to need still a 2 here that I can factor out. So I need 3x squared to be 2 tan squared theta, so that I can factor the 2 out and get 1 plus tan squared theta. But if 3x squared is 2 tan squared theta, that tells me that x squared is 2/3 tan squared theta, and x is the square root of 2/3 tan theta. Sometimes these things aren't as, the constants aren't going to be perfect. So let's save that because we'll need that for later. X was square root of 2/3 tan theta. dx then is the derivative, that's just a constant, 2/3 derivative of tangent is secant squared theta. What else do we need? Well, now we can finally say that this denominator, 2 plus 3x squared, is 2 plus 2 tan squared, which is 2 times 1 plus tan squared theta, which is 2 times secant squared theta, because 1 plus tan squared is secant squared. So if we put all this together, the only things that we actually need here are the bottom two to change the integral. If we put all this together, our integral becomes 1 over the denominator, which is 2 secant squared. And dx, we also just calculated, which is the square root of 2/3 secant squared theta d theta. I forgot to write my d theta there. And again, something that we've seen happens, the secant squareds cancel. And this becomes integral of 1/2 square root of 2/3 d theta, which is 1/2 square root of 2/3 theta plus c. And finally, we need to know what theta is, but that's why we'll go back to this equation. If I solve for theta, I get square root of 3/2 x is equal to tan theta, so that tan inverse square root of 3/2 x is theta. And it looks messy. And really the only thing that's messy about it is the constants. But that can happen when we have a mix of the two different types. All right, so that's all we need to say about trig substitutions right now. We'll see you next time.